Okay, 2.6 is all about piecewise functions. So these are functions that are defined by in different intervals of the domain by separate functions. But before we can establish that, let's talk about what it means to be continuous. A function is continuous if it can receive every input from a certain domain. We can tend to think of this as if it can be drawn without picking up your pencil. It really also needs to be going to the same point on both sides. For example, asymptotes aren't continuous because they're breaks on the page. Most of the time, piecewise functions are discontinuous at the point in the domain where they change from one function to another. This cannot always be the case. If they happen to be at the same point, they can be continuous, but it's usually not the case. Now, to be continuous on an interval, we can say a function is continuous over certain areas or intervals, even if it's not continuous over the whole domain. So determine the intervals of the domain over which the function is continuous. This looks like the right half of x squared. So could you draw that without picking up your pencil? Yes, but only over from, it looks like 0 to infinity. If you're at an endpoint here, you only needed one-sided continuity if there's nothing happening on the other side of the domain. So from here, I would say it's continuous from 0 to infinity. We only have one-sided continuity at 0, but that should be fine unless there's another function going on over on the left. If there's another function on the left, we may not be continuous at 0. Whereas down here, it looks like we're continuous from negative infinity to infinity because you could draw this whole thing without picking up your pen. More importantly, it looks like the function is defined everywhere and it follows one single value. Now, before we go into piecewise function, let's talk about all the possible parent functions we might need. So f of x equals x, we should know what the y equals x line looks like. It should be a line with a slope of 1 through the origin. Generally speaking, the domain and range of a linear is negative infinity to infinity for both of these. What about f of x equals x squared? This is our parabola. The thing about our parabola is it still has a domain of negative infinity to infinity. Any x value can go in, but our range, our outputs are from 0 to infinity. You only get non-negative numbers when you square. F of x equals x cubed. Looks a little like x squared, only remember that if an odd number or a negative number is cubed, it's still negative, so instead of going up on the left side, it will now go down, and it's a little bit steeper. For f of x equals x cubed, and for x to any odd power in general, the domain is negative infinity to infinity. The range is negative infinity to infinity. The square root of x. So the square root of x is a little bit different because what numbers can we put under the square root? For graphing purposes, only non-negative numbers. This looks kind of like a parabola on its side, but only half of it because it's only the principal root. In this case, our domain here is from 0 to infinity. Our range is also from 0 to infinity. The cubed root of x is the inverse of x cubed, so it looks a little similar, only it's like a reflection a little bit. It looks kind of like lying down. Instead of going up and down, it's going way out to the sides. But odd root powers, just like odd powers, domain and range are negative infinity to infinity. Absolute value of x, most of you know what this looks like. These look like of the V shape. Going through the origin, because remember, what does absolute value do? Changes any negative numbers to positives, but it doesn't do anything to positive numbers. So our domain here is negative infinity to infinity, but just like x squared, the range is only 0 to infinity. Now, most of your piecewise functions will use only basic functions like linears or constant functions, but on rare occasion, it could use other functions, potentially these parent functions, but if it uses one of the complicated functions, it almost only uses the parent function instead. So then, what is a piecewise function? We talked about it a little bit at the beginning. It's a function defined by different equations over different intervals in the domain. It may or may not be continuous at the boundaries. So evaluate the function. Let's just talk about what this function looks like. F of x equals 2x if x is less than or equal to 0. So if you're plugging in an x value that's less than or equal to 0, you plug it into the function 2x. However, if your x value is greater than 0, you're going to plug it into 1/2 x. So what does that mean? Well, it says evaluate the function at 3 and negative 7. Is 3 less than or equal to 0 or greater than 0? 3 is going to go in here. However, negative 7 is less than or equal to 0, so negative 7 goes in here. So when evaluating f of negative 7, we'll plug it into 2x, so 2 times negative 7, which is negative 14. But for 3, f of 3 goes into the second function, 1/2 times 3, which is 3/2. So on a graph, this will look like different pieces of the graph. They'll be broken up at this 0 and do different things on either side. Let's just try again, evaluating functions. Now this piecewise function has 3 different parts. F of x equals negative 2x plus 1 if x is less than or equal to 1, 4x minus 2 if x is between 1 and 5, and x plus 2 if x is greater than or equal to 5. Okay, so let's just find which function each of our values is going into. Negative 3 is less than 1. So this f of 1 is our boundary. To know which one this is going to go into, you find the one where x is equal to 1, so that less than or equal to 1. So 1 goes up here. F of 3 is between 1 and 5, so it goes here. F of 5 is our other boundary. Where's the equal sign with the 5? It's down here. So 5 goes in the third equation, and 10 is greater than 5, so it also goes in the third equation. From here, it's just plugging in. F of negative 3 goes into the first equation. Negative 2 times negative 3 plus 1. 6 plus 1, which is 7. F of 1 goes into that same equation. Negative 2 times 1 plus 1. It's negative 2 plus 1, which is negative 1. 3 goes into the second equation, so f of 3 is 4 times 3 minus 2. 12 minus 2, which is 10. But 5 and 10 go into the last equation. So f of 5 equals 5 plus 2, which is 7. And f of 10 is 10 plus 2, which is 12. And we will do more with piecewise functions and graphing them in the next video.